Hi everyone, in this video we will be designing a ticket booking system like Ticketmaster. The outline will be as follows. We'll start with the functional requirements, then the non-functional requirements. After that we will see the core entities of the system, API design, high-level design, and then the deep dive section. So let's start with the functional requirements. First, the user should be able to view an event. Second, user should be able to search for an event by venue, by performer, or by some metadata that is related to event. So we want to provide a full text search to the user. Third is the user should be able to reserve a ticket. So reserve or book a ticket is kind of the same action for us. Next are the non-functional requirements of your system. The system should scale with the increase in load. So if the load on the system increases, the system should still be able to work in an efficient manner as expected by the user. Next is we should be able to prevent double booking or overselling of tickets. So if we have 100 tickets for an event, there shouldn't be any scenario that 101 or 102 people have booked the tickets or a single ticket is booked by multiple user, which will be wrong for our system. Next, we want to provide the user low latency search. So if there is a very famous concert coming up and a lot of people are searching for it by some keyword, then we should be able to provide low latency search to the user. Fourth one is support heavy read nature of the system. So the system in itself is a very read heavy system as opposed to the write heavy system, because a lot of people will be coming to your website or to your system for getting the details of an event, what event is happening and where it is happening, who is the performer, what is the venue, and all those sort of things. Next section is the core entity section. Let's start with the event entity. So event entity will capture everything about an event, where the event is happening, that is the venue, where who is performing in this event, how many tickets are there, what is the address of the event, what is the duration of the event, and so on. Next is the booking entity. So a booking entity will have which event was booked by whom. So who was the user that booked this particular event will be stored in a booking entity. Next is the user. So user is the one which is browsing through your events, selecting the tickets, booking the tickets, making the payment, and also of things. Next is the ticket. So a ticket entity represents entry to an event. So this ticket is basically a ticket to an event, if I say. And yeah, ticket will contain who is the owner of this ticket, to which event this ticket was booked for. Next up is the API design section. So we have an interview template, system design interview template video. I'm following the same template here in this design. And API design, we start by defining all the functional requirements. So you take one by one your functional requirement, map it to an API endpoint. So we start with the first functional requirement, which is view an event. So we will create a get API for this. So you see we have versioning here, v1, and we have the event ID as the path parameter here that we have specified inside the colons. So our API endpoint is a get type /API/v1/events and then the event ID. The response will be as follows. So we will give the venue, LA, for example, I have taken here. Who's the performer? And cut that part. Who's the performer? And like Taylor Swift is the performer here. Next is the tickets map. So you will return a list of tickets that will have like the seat number or some other detail. If you want to have things like, hey, this ticket belongs to this area of the venue, which is priced slightly higher than any other area. So all those information I haven't mentioned here, you can put anything in this particular list of JSON objects. Second functional requirement that we had was searching through an event or searching for an event. We'll create a get API here as well, which will be /API/v1/events/search, and with query parameters of queue, which will have the query that the user provides. So the user can search for something like Taylor Swift. So that will be the query in this case. How many results do we want to provide? So this is an important part. We should be thinking about pagination over here. Pagination because we do not want to return the entire result set at once in the response. That will be very heavy to fetch in the database. Very heavy response will be going through the front end and it can be really slow. So we implement a pagination based on the page and the size. And the response for this API will be the list of events and it will have event details inside it. So I haven't mentioned the event details on purpose because this is not an API design interview. It is a high level system design interview. But if you want, you can mention but all details in the event will be there. So since we have taken event as an entity, you can define your event attributes with itself, and then later here you can just mention I'm going to return that event entity. Next is the reserve a ticket. So this is our third functional requirement. So we create a post API here because the user is making a change so that they can book a ticket for an event, and as a result a new entity will be created in the database. So that's why it's on post API. The API endpoint looks something like this. So we have /API/v1/book or /reserve you can also give here, and then the event ID. And in the request parameter you will have list of tickets that you want to book. So you can like book multiple tickets at once. In case you want to do that, you can select multiple seats if it is if you are designing a system that involves booking a ticket for a movie, like BookMyShow or something like that. This is a generic design not tied to like specifically Ticketmaster or something like that. So you can book tickets for movies and multiple seats you can select from the seat map and send it to this API. So this API is quite extensible over here. You can send a single ticket as well as multiple list of tickets. The response will be just 201 created, and 201 is the status code for created. So we will return that. You can return some response like you can return the booking ID if you want. So but this is also fine for interview perspective. Note that the reserve and confirm is a two-step process. So a user will reserve a seat and then eventually they will go ahead and make the payment of that particular seat, confirming the tickets after making the payment. So it is a two-step process. We only show a single API because maybe the payment process is being handled by a different API, some external API gateway you might be using over here, like Stripe, for example. Next is the high-level design. So in high-level design also we follow the same technique that we mentioned, that you take your functional requirements one by one and then you start evolving your design in a scenario. You start creating all those boxes, all those services that you want in your design. So we start with view and event. So for view and event, we will have a user over here. The user will make a request to the API gateway. The API gateway will do the routing, the load balancing part. So that is what is being handled by an API gateway. It can also handle security like authorization and so on. Now we create an event service for this specific purpose, and the event service will be talking to the database for getting an event with an event ID. Next design that we have is search for an event. So for searching an event, we will have a search service. The reason why we are creating a separate service than an event service, you might be thinking that, hey, an event service can do the search part, but the scaling needs of both of these services are quite different. Maybe you are getting very less request for a search. So only a few users on your app or your website are searching for an event. Most of the people are seeing the famous events on the homepage itself and they are just clicking that. And as a result, the way you will scale your service, the search service and event service, will be quite different. That is why we have separated them out in a different microservice so you can scale them differently. If there are, like for vice versa, a lot of search requests coming to your system, you can scale the search service independently without being dependent on the event service thing. Next requirement that we had was reserve a ticket. So for reserving a ticket, we have created a reservation service over here, and that's how our high level, very simple design looks like. This design, I know, have a lot of loopholes, and yeah, but it is a working simple design. It is highly advisable that before you start deep diving into multiple sections, you basically create at least this bare minimum design which is correct in the sense that it works. Maybe it doesn't scale, maybe it isn't like highly available, fault tolerant, and low latency sort of a system. But that is what you want to focus now in the next part of the interview, which is your deep dive section. So in the deep dive section, we start with our non-functional requirements. We take our non-functional requirements one by one and we present them as a deep dive. So here you would have to, initially when you are designing your NFRs or non-functional requirements, your NFRs should be in a way that in line, it should be in line with the interviewer, that they should give you a go ahead, like this NFR looks really good to me, these are the part of the system that I want to focus upon, and hey, go ahead with this. Because you should keep in mind always while designing your NFRs that later in the deep dive section, that is the most important section of this high level design interview. For every high level design interview, the deep dive section is the most critical one, that decides if you will be able to make or break in the interview. So make sure you lay out your NFRs in such a way that they give a lot of weight to your interview, they show your technical skills in a good way. And yeah, so we will be starting now with the deep dive. So first deep dive will be system should scale with increase in demand. This was our first non-functional requirement, and we see there are two problems in the system, the event service and the reservation service, which might be under a lot of load. If you have like a Taylor Swift event which is really popular and millions of people are trying to book tickets for that event, then the two services inside your design, the event service and the reservation service, will mostly be under very heavy load. So these kind of are like single point of failure. If any of the service goes down or it's become slow, it is having a high latency, the entire website could crash, right? As a result, what we will do, we will try to improve both of these services, the event service and the reservation service. So in order to improve the event service first, we will move ahead and we will cache some of the details of an event. So if you are getting a request to get an event by an event ID, once an event is created, it's not going to change much. So it's like the amount of writes or the amount of modification to an event once it's created is really low as compared to the amount of reads that the user is performing on it. So multiple users are performing read on an event that, hey, this Taylor Swift event is there, I want to get its detail, I want to reserve a ticket inside that. And so if you put a cache over here and cache the event details by event ID, or maybe you can cache your API's first list of events. So you can have a most popular section, something like that, hey, these events are really popular. So you create maybe a separate API for getting the popular events, or you have a parameter in your API for only the popular events. And by that way, you can also cache these popular events, which you can later return from the cache like very efficiently. You don't have to go to your database for that. And in case it modifies, then you have to handle the modify scenario. The modify here is simple. You update it in the cache, and then in the database you can do a write back, write through, write aside. Because the number of writes are not very frequent, that's why I'm not very worried about the write part. And you can keep the TTL high as well here, because the chances of getting an event modified is very low. And the next problem is the reservation service. So for the reservation service, what we can do is we can have a virtual waiting queue and a consumer. So a virtual waiting queue can be something like, you can use Redis streams, or you can use something like Kafka. I would highly recommend using Redis stream kind of a scenario here. You don't want a lot of persistence, or I don't think you want retries that much over here in the virtual waiting queue. So it is a virtual waiting queue. Your users will eventually drop off from the system, and this is only going to come into the data flow path only when certain threshold of limit is reached. Then you will start putting the requests from the reservation service into the virtual waiting queue. And you put the events in the virtual waiting queue. On the other side, you have a reservation consumer. So a consumer pulling data from that queue and processing the reservation requests. And as a result, what happens is this also can be a feature to your system. You can show that, hey, you are waiting in the queue for the reservation and you are this much behind other people. You can do that by offset if you are using Kafka here. So you can see the offset, where the most recent offset is and what this particular payload was inserted to, what is the offset of that message. So this can be a feature for your system as well. So you can use a virtual waiting queue and a reservation consumer. This will decrease the load to the reservation service because we have a path over here that is hitting the database every time, and this is expensive. I'll tell you that this is expensive. This path that we see from the reservation service to the database is expensive because we are next going to look at the double booking prevention, and here you will learn that why that path is expensive. We have locking and stuff over here, you will understand now. So option 1 is pessimistic locking. So what I mean by pessimistic locking is basically a select for update. So if you don't know select for update, you can definitely go ahead and read about it. So it is a simple operation in a database. Your MySQL 8 has it, your Postgres must be having it, and a lot of other database provide a similar operation to select for update. Select for update means that you're selecting a few rows, you are applying a row level lock over there. You are applying a lock to those rows. So hey, you are basically saying, hey, I want to update these rows, just make sure that no one else is updating these rows while I am updating. So it is like a critical section sort of a scenario where you are updating and you don't want other people to come in and update and have the system in an inconsistent state. How we are going to do this, how we are going to prevent the double booking scenario using pessimistic locking. So we begin at that part. We begin a transaction. So transaction in database is like you have multiple set of queries. You have 3-4 queries that you want to execute, but you don't want to end up in a scenario where either 1 or 2 queries are executed and the third query is not executed. So it basically means either all of the queries will be executed or none of the queries will execute. So if a few queries are executed, there will be a rollback, and that's how the transactions in a database works in a nutshell. So you begin a transaction, you do select from events where event ID is equal to 1 and ticket ID is something like 123 for update. So this will acquire lock to those entries. So there will only be one entry for this in the events for this ticket ID. You'll acquire a lock over there. You will update the events table again. So here you can see you did select for update, and now you are going to update. You are going to do the update operation. You're going to set the status to booked, where the event ID was equal to 1 and ticket ID is equal to 123. So this is after the user has made the payment. So once the user makes a payment, you execute this particular transaction. Or what you can do is you can do a select for update and then wait for the user. So idea here is you do a select for update, you reserve those tickets, and then you do an update and you wait for the user to make a payment, and then you end the transaction, you commit the transaction in a way. The problem here is that there will be contention, because contention means that you have a few rows. So let's say you have 100 tickets for someone's event who is really popular, and millions of people are trying to book those 100 tickets. So in that way you have contention over those 100 rows. Everyone is trying to acquire a lock on those set of rows, but you have only a limited number of tickets, or limited number of tickets in the database, in the number of rows. As a result, there will be contention. Everyone will be trying to acquiring that lock, so it will hit the database really hard and it can become really slow in that scenario. The second risk is the risk of tickets being locked infinitely. So something like a scenario can happen where you do a select for update, you go ahead and mark the ticket as booked, but the user now says, hey, I want the refund, or maybe the payment didn't go successful and you updated it to booked. In that case, it will be forever logged into a booked status, which will be a problem for our system. And you will have to manually intervene here to fix the system. There's no other way around that. So option 2 for us will be the status plus expiration time. Let's see how this works. You start a transaction again. If the status is available or reserved and the expiration time, so you have now, instead of just the status available in the events table, you will have now two columns in the events table apart from the other columns. You can have other column like event detail, performer, or the ticket ID, and all those sort of things, the details related to an event. And you will have two more columns which will be status and expiration time. Updating a ticket, how it happens is you check, you do this select query, and whatever IDs of that particular ticket you will get. So here you are doing status available on a ticket, so you will be sending a ticket ID or an event ID as well, and you will get the row where this condition is true. If you don't get any output from the select query, this simply means that hey, all the tickets are booked, or the ticket is under a reservation right now. It is under a reservation time. It hasn't, the reservation hasn't expired till now. So hey, I can get this ticket, right? And this thing that we have over here is, if it is available or reserved, the reason why we are doing a reserved here is because we have an expiration time, because someone can come in and reserve a ticket, and we can reserve it for X minutes. The X can be decided here, like for 10 minutes we want to reserve a ticket. Once the user goes in the UI that hey, you select the ticket and you press the next button, hey, this ticket is reserved to you for 10 minutes. You have 10 minutes to make the payment. If you don't make the payment, the expiration time hits and someone else would now be available to book a ticket. The second, what we do is, in case the user was successful to reserve and make a payment in next 10 minutes or whatever time we choose, we update the event table and set the status equal to booked, and the expiration time also we can set to whatever, it doesn't matter. Once your ticket is booked, the payment is done, it is with you. And what you can do in case of a reservation kind of a scenario, you update the status to reserved and you set the expiration time to now plus whatever, let's say 10 minutes. So it will be reserved for you for the next 10 minutes. And then you end the transaction, of course, or commit the transaction. Problem with this approach is that slow read operation because of condition. You have introduced another query over here that hey, before I go ahead and reserve something, I want to do a select query now. So you do a select query, you get something, then you update it, right? So this is an issue. The reason why it's an issue is because you have introduced one more query, you have a lot of load on your system already, and you are having one more query. In that scenario, it is slow or fast, that doesn't matter. But here you are doing an update and a select query which is going to slow down your database, and it is also acquiring a lock over here. You are doing a transaction in here, and during the update there will be a lock acquired on that particular row. And also, just one more thing I want to point out, when you do this status available, expiration time greater than now, here also you will have to do a select for update, because you don't want two people to get a status available and expiration time greater than now and then update, do like a double booking scenario. So you will have a select for update in this case as well. Next approach. So next approach for preventing double booking is the distributed lock method, and this one is the most sophisticated one. This is the solution if you want to prevent double booking. You have to choose this one. How we are going to do this? So when the user clicks the ticket, what you do, you create an entry in the distributed cache. You can use something like Redis or any other distributed cache system like Aerospike you can use. And with the ticket ID and the TTL of let's say 10 minutes, you can create an entry inside the distributed cache that hey, the key is the ticket ID, the event ID plus the ticket ID, and the TTL of this is 10 minutes. If the user completes the payment, then you update the database. So till the second point where you create an entry in the distributed cache, we haven't like done any update in the database till now. We haven't marked something as a reserved or something like that. We have just created an entry in the cache. If the user completes the payment, then update the status in the DB database as booked. right? This is how your thing will work. And before we go on to the section, I just want to mention that how you will be checking if a ticket is booked or not is by the entry in the distributed cache. And if you see an entry missing in the distributed cache, you have to also look at the database. So if it is a cache miss, if it is not resolved till now, you have to see in the database that hey, this ticket is booked. One way to optimize this path would be to maybe cache this booked status as well. So you can cache the booked status into a cache system, and instead of checking every time in the database. So once you have booked the ticket, the only operation that can happen is a cancellation if you allow it. So once it is booked, there are 90% chances that it is going to stay booked. So the status is not changing as much. As a result, you can cache this particular thing as well. The problem here, of course, this also has a problem. There's nothing in system design without a problem. The problem here is data loss in cache will result in dropping all reservations. So if your cache goes out, it gets deleted, the system gets restarted, your cache is in memory store, you are not persisting it. In that scenario, what will happen is all the reservation that were active at the time would now drop off. This will be a bad user experience. Of course, you can have workaround with this, but that will involve increasing the latency. So we will have a trade-off over there, that we will increase the latency of the system if you want to have a workaround against this. But I think for most of the system it is acceptable that hey, reservation dropped for you for whatever reason, please reserve it again. Next, we are going to see that we have now implemented this reservation log in our design. So this is the log that we have talked about. This is the distributed log option, which was the third option that we discussed. So we will put the reservation related stuff here, and this we can use as a distributed cache for reservation. So you don't have to hit the database, acquire a log over there. Next up is the low latency search part. So for low latency search, what I'm going to do is I'm going to have a search built, search purpose based built database like Elasticsearch or OpenSearch you can use from Amazon. Elasticsearch is pretty cool. You can do full text search. It has your inverted indexes. The full text search is really fast. It indexes everything in the RAM. And how you are going to set it up is in such a way that your event database is going to have all the events. Whenever there is an insert operation, there will be a CDC pipeline that will be triggered. A CDC pipeline is change data capture. You can look at it about more in the detail, but here you simply means that there is some sort of way of syncing your traditional MySQL, Postgres, or like any relational database events. So any updates, any writes to your database will simply trigger an event, and it will write an entry inside the Elasticsearch. It can write an entry inside a queue, a Kafka queue, for example, and then from Kafka queue, you can write your own consumer, you can do transformation stuff, and then persist it in Elasticsearch. So this is how you have like already built in connectors. You can have plugins for your database that syncs automatically to Elasticsearch. A few famous ones are Maxwell, I think. For MySQL, it reads the min log and sends the message as a JSON to a Kafka queue or whatever you configure it to. So Maxwell is one of the tool that you can use for CDC. But the simple thing is you have the data now in the Elasticsearch. It is indexed. You have created the mapping and all. Now you can perform the search query over Elasticsearch. Another thing that we can do here is we can cache your search query. So if everyone is searching for Taylor Swift event, you can cache that search query that hey, Taylor Swift, give these results. Now the thing here is your cache should have a low TTL over here, or not a like great TTL like we kept in the event service. The TTL should be low because maybe there are new events added very frequently and you don't want to miss it in your search, or you can invalidate the cache whenever you send like any event that you see something like hey, I'm having this performer Taylor Swift or someone else's event and I want to show it in the search result. You can invalidate cache that is mapped to a key of Taylor Swift, and then it will start picking up from the database itself and then cache it again. So this is one part. This was our read heavy non-functional requirement. So we had a non-functional requirement about read heavy scenario, how you will handle the load under read heavy scenario. And what is next is you can also have a CDN, which plays a really important part. So you can cache your entire homepage, or let's say there's a most popular event section which you show right there in your homepage. You can cache the events as well there, event, so your user won't be hitting even the API gateway or the event service. It will directly see the popular events from the CDN and return it to the user. Of course, you are going to have a lot of metadata here, like pictures of the events or pictures of the performers that you have to also keep in the CDN cache, and some sort of a blob storage like AWS S3, and then you will eventually serve it from cache like CD. Yeah. So that's it for this video. Thanks a lot for watching. If you have any system design interview questions that you want me to cover, or you have any suggestions for any improvement, do share it with me. And that's it for the video.